Hi there! Our topic for today is continuity. Okay, what are we going to talk about in section 2.5? First, let's look at the graphs of continuous and also discontinuous functions. And then we'll use the definition of continuity in terms of limits, because remember, that's all we've been talking about for the past few weeks. And then we'll use the continuity test to determine whether a function is continuous or not. And if it is not continuous, there are different types of discontinuities. And then we'll talk about properties of continuous functions. And finally, we'll discuss intermediate value theorem. Oh, such a cute puppy. How big will your puppy get? That's the question here. Well, because it turns out that the growth pattern of dogs is a continuous function. So we will be able to determine what will be the weight of your puppy after 2 years, right there. So depending on the breed, then that's where you will find out if it's a big dog or an itty-bitty dog. That's going to be its future weight. And of course, its weight in between 0 to 2. Let's say at 1 year or at 18 months, and so on and so forth. It's just an example of why we use continuous functions, because it occurs every day and everywhere. Here is another situation, another example of a continuous function. Let's say you are on top of a tall building, I guess, and it's 500 meters high, and then you're holding a ball. And what you want to do is to find out the distance that it traveled from the top of the building until, of course, it reaches the ground. Say, let's just do it in slow motion. We're going to drop the ball. And at different points, we will measure the distance it's traveled from the top. We measure it from here. That's actually our zero distance all the way up to 500 meters that it elapsed in 10 seconds. And it turns out that it follows this pattern. How about we talk about a continuous function in terms of its graph? Suppose you have a continuous function on what we have here is a continuous function from A to B, and suppose I plot right there. That's the point at x equal to a. The function value is at this point. And then as long as I keep or stay on the screen or my tablet and will not lift the pen, then we have a continuous function. That's all there is. No jump, no gap, no holes. So what do you think is a discontinuous function? Well, it's the opposite, which means, say, suppose I started off here. Somewhere along the way, I jumped and then continued on up to B, x equal to B. There we have a discontinuity at, say, call it x equal to C. Because there was a gap, I lifted the pen right here and continued on down this way. Then we have a discontinuous function. So now, what does it mean in terms of limits for a function to be continuous at an interior point? That means it's in the open interval, say from A to B. And let's just take a generic interior point, x equal to C. And then, say the function value is right here. Let's call that, say, L, or just say f of C. Right? So suppose the graph looks like this. Then, if we say that a function is continuous at x equal to C, if the limit of f of x as x approaches c exists, that means it exists both sided limits on left and coming from the right, and in particular we have a continuity if the limit value is in fact the function value itself, f of c. So if this is the situation, then we have a continuous function at the particular point x equal to c. Now, what does it mean in terms of limits for a function to be continuous at the endpoints? So again, take a look at our graph, and it says we want to find out what is the definition of a continuous function at its endpoint, say from at A and at B. Then because, that's why we already used the one-sided limits, that means let's go ahead and write the function value first here. It's f of, right there, it's f of A, and then right there, let's call it somewhere here. Let me just plot the point because it's too far out there. It's the point B, and the function value there, of course, is f of B. So in this case, so f of B is somewhere around here. Right there. Okay, that's f of B. And then if we write the ordered pairs of this point, it's at A and f of A. Okay, so now the function f is continuous at its left endpoint if the limit f of x approaches A coming from the right. See, because all the values are coming from the right, and you see that the function is values converge to or approach f of A. And then on this other side of the endpoint, of the right endpoint, if the limit of f of x, this time we let x approach B from where? From the left, because we're coming on the right side, right hand endpoint, then all the x's are coming in from the left, then the y values approach f of B. So definition, we have a function is continuous at an interior point, like we said, if the limit exists at x equal to c, that means both left and right limits exist, and or it's one-sided limits, and it's in fact equal to the function value f of c. And of course at the endpoints, okay, there's your A, there's your B, then we say that the limit of f of x as x approaches A coming from the right, and it's equal to f of A. So there's our f of A. And of course, the limit of the function as x approaches B coming from the left, the y values approach f of B. So I guess it's right here. Let's extend that right about here, f of B. Continuity at a point. Let's look at example 1 on page 76. Find the points at which the function f that is in here, we have this piecewise function, and find out at which points is the function continuous and where it is not continuous. So let's go ahead and look at the points at which f is continuous. Well, take a look at the interval for which the function is defined. So here, the domain of this function is from 0 up to 4. Okay, so let's go ahead and write that down. The domain is from 0 to 4. So let's look at then the endpoint, the left endpoint. At x equal to 0, because it's an endpoint, then we just look at the limit of f of x as x approaches 0 coming from the right. And we see that as x approaches 0, then the y values approach 1. At the same time, what is f of 0? F of 0 turns out to be equal to 1 as well. So you see there, they match, the limit value and the function value match. Now another point where the function is continuous is that we can look at is at x equal to 3. It's an interior point, so we look at the limit of f of x as x approaches 3. So on both sides of x equal to 3, the y values approach 2, which in fact is f of 3. Okay, and of course, all the points in between, okay, all the points in between, except where we exclude 1 and we exclude 2. But all the interior points, so if we look at, say, let's try this, then at interior point, the limit of f of x, as x approaches c, is equal to f of c, except where, of course, except 1 and 2. So then we can now tell you where else it is not continuous. So where the function is not continuous is, as you can see, at x equal to 1, 2, and 4. Why is it the case? Because the limit of f of x as x approaches 1, all right, coming from the right, or let's just start coming from the left. Coming from the left, it's equal to what? 0. And then the limit coming from the right as x approaches 1 from the right is, okay, my x's approach 1 from the right, and the y values are at 1. You see where these do not coincide, then we know that the limit does not exist. So the limit of f as x approaches 1 does not exist. Okay, now let's look at x equal to 2. Well, we can see that there's just a hole there, so indeed we have a limit of the function f of x as x approaches 2, and it's equal to 1. However, the problem here is that what is f of 2? Our f of 2 is 2. When the limit and the function value are not equal to each other, then we don't have a continuity, because the hole remains there and you have a function value somewhere else. The same thing at an endpoint. So we look at the limit of f of x as x approaches 4 from the left. Because I'm approaching 4 coming from the left, the y values approach 1. Now what is f of 4? Well, let's estimate that. It looks like f of 4 is 1/2. And again, they're not equal to each other. So the same case as 2 and 4, except this you have an endpoint limit, so it's a one-sided limit. And these are actually trivial because, of course, to the left of 0 and to the right of 4, the function is not defined there. It's not in the domain.